Good morning, everyone, and thank you very much for taking the time today to join this, let's say, second part of our webinar. Yesterday was on electrical submersible pump, and today is on gas lift operations and troubleshooting. It's because those two gas lifting systems are the more common we have in the oil industry. And then we may find PCPs and jet pumps and whatever. But I think those two ESPs and gas lift are the more used in the oil industry. So based on that, we wanted to share some ideas and knowledge on those systems. So the agenda for today is the gas lift fats. The tubing performance curve is just a brief, introduction on this gas lift advantages and disadvantages, optimization, troubleshooting in the three areas, which is the inlet, the outlet, and downhole problems. We will define those later on, and tuning the well and gas lift design example. With this, we will go to gas lift fats, and so something to bear in mind: constant flow gas injected at high pressure is required. That's always, if we are planning to have a gas lift system, the first the first question to be answered is, do we have a permanent, source of gas? Yeah, and also should be at high pressure. So, which is the main source to lower the intake pressure. And so also the formation pressure. That's the key point in the continuous gas lift, which is the one I'm talking about. Not intermittent. The lift supply pressure should be constant, of course, and the high quality of gas also should be, some of the major requirements. Without this, we are facing too many problems, and we are not producing an optimum rate from the wells. Generally, the optimum volume of gas to be injected is determined by well test. The well test is basically the tracking of the volume injected, gas volume versus the production fluid. We will touch on this. And when having a large gas quantity present in the production flow, it leads to lowering fluid production due to increase in the borehole pressure. Yeah, the increase of the friction pressure loss caused by the increase by the higher gas production also increases the borehole pressure, which is something we are trying to avoid. And so by doing this, we are lowering the fluid production. We are decreasing the production, so we are in the wrong way. So we have to be aware of, the how much gas is producing after through above the injection point. So of course, each well has the optimum gas lift injection rate. But when we are dealing with the entire network at the field, the optimum gas lift injection, of course, differs from the particular well. So we have to define if we are optimizing well by well, or we are dealing with a whole system, a unique system. So I was saying that it's different when we are dealing with the optimization of individual gas or well by well or the entire field. So the idea is to define if we have a system, a central system, a gas compression, and we are distributing along across the field. We have to bear in mind that we have losses along the tubing, and so the wellhead pressure for the wells are different. So those considerations should be taken in account too, in order to really optimize the productivity from each well. Here is just a tubing performance curve, just to discuss some ideas around this. Here we have the outflow of the tubing. So in this case, here we have the minimum rate for a stable flow. So it means everything to the left of this curve is leading to accumulation of liquids in the wellbore. So here the pressure drop is coming from the liquid buildup. But to the right of this curve, this point, the minimum point, which is the stable flow, we have pressure drop due in the tubing due to the friction. So the more we are having gas in the, if for instance, of course, with the production, the gas from the reservoir is increasing. So the original calculations we made, the gas is changing. Remember that, everything subsurface is changing, the pressure is changing, the gas liquid ratio is changing, the GOR is changing. So we have to have in mind this. So in order to avoid this situation, in a point, the production, the pressure loss produced from the gas production is too high that is not any more effective or optimum for the gas production. So the idea is produce the minimum rate, but without the excess friction. That's the message here from this. So some advantages, of course, I think is one of the unique systems to handle sand or solids. Yesterday in the ESP system, we mentioned that one of the problems with the ESPs is any sand or solid production will be catastrophic for the ESP. In this case, we are not having any problem. We are not having any pump or something like that. Just so we are able to produce sand or solids. We can use this system in highly deviated wells, or even especially offshore. We have a lot of directional drilling wells. So this is one of the optimum artificial lift system for that environment. Another positive thing from this system is that anytime we can run one-line tools, to perform some repairs through the tubing, which is not nothing that we can do with any artificial lift like pump, any pump in the well, unless in the case of the ESP we have a white tube, but in other conditions we cannot. We have to pull everything just to make some, for instance, logging. Another point is allow flexibility in terms of depth and volume to be produced. Of course, we will see that we have to, once the optimum gas depth is defined, the condition of the well, our reservoir are changing. So in a moment we had to go back and redesign and trying to get the injection point a little bit deeper to continue producing an optimum volume. The centralization of the gas lift it will allow to lower the capital cost, and so the well testing and well control is the downhole equipment is not too expensive, and we can easily pull and repair or replace anytime. This is very gas, if you are not doing the best or the optimum design, still you have good results. It's not like other system. If you didn't, consider, the whole information, maybe you are not designing the optimum conditions of the well. So in case of an ESP or PCP, you are in troubles. In this case, I mean, you are still having good results. So disadvantages is relatively inefficient. Often, of course, you or the company invested a lot of money, and we are not getting the optimum production. Any high back pressure, which is some requirement for this, because you need to have a high pressure injection. So in this case, we are killing ourselves. We are restricting the production in a continuous gas lift. So in that case, we are, of course, increasing the borehole pressure, which is something we are not looking. We are looking for lowering the borehole pressure, which is the only way to increase the production of the well. Another point is the gas lift supplies, should be for the life of the project. So the increasing water cut, also increase the borehole pressure with a fixed gas lift pressure, which is the design we originally we made. So some water cut, another type of artificial lift might be like ESP, which handles a lot of high volume, should be considered in this case. So to be honest, most of in the mind of the companies, gas lift is not the only artificial lift for the whole life of the project. They are aware that in a point you need to continue decreasing the borehole pressure or the reservoir pressure. So this is not the system we will allow to do that. So you have to migrate to another type of artificial lift. Of course, it's expensive maintenance of a compressor. Oil, heavy oils, less than 15 API. Of course, we are facing high friction, and the cooling effect of the gas expansion also make this problem, increase. Also, the cooling effect will, of course, exacerbate, let's say, any potential paraffin problem that we have in the well. So those considerations should be really considered before we decide, or the company decide to go for this system. For low fluid volumes, higher quartz is not the most efficient type of artificial lift. The gas lift, we will touch now in the gas lift optimization. The optimum production by gas lift, as it's a stable rate, produced by specific gas injection rate, which is the way we produce a optimum production, sustained for a long time. That's the ideal of the gas lift injection. Now, are we able to achieve this? It depends on many issues, like gas, as I mentioned before, the quality of the gas and the volume and the compression and everything. So this, and the type of fluids we are getting from the reservoir, probably the water cut initially is low, but with time it is increasing. So those considerations are involved in this, optimum production. Generally, the optimum amount of gas injection, of course, as I mentioned before, is the best way to define this is by well test. So you start with the low rate, and I'm talking about injection gas, and then you get the production, and then you plot, continue getting, increasing the gas until the production is stable, and you measure the volume, and 4 or 5 times. In this way, you get the optimum gas injection. This is nothing that you can calculate, and you say this is the gas to be injected or used, and we are getting the optimum. It's not like that. So of course, another way is running this exercise in Prosper. So the way of to optimize is as I put it right here, at least 4 points in the curve performance. You draw tangents to each point, to rate versus gas injection. You have to generate the slopes of those at these tangent points, and the slopes are plotted versus gas injection rate. I will show here. What I mentioned is here you have for each, this is one test here, a gas injection volume, and you get a production. Then you, of course, you have the you have the tangent point to that, and then you track this tangent, and then you increase, after the production is stable, you increase the injection of the gas and get an additional oil production, and you continue the process. And for each point, you are reading the tangent section for each point. At least, again, this is at least 4 or 5 times 4 points. So the slope of the plot here is defined as M, which is a function of the gas lift cost and the oil cut and the profit per barrel. So this is an economic evaluation, which is something that the managers should looking for. This is based on, again, economics. Of course, gas lift cost is something that should be defined, or should be, have a knowledge in the company. So if this is the original one, so we have to get reference from other operators, something like that. Of course, the profit per barrel is also depending on each particular field. So that's, but anyway, with this information, we plot right here, we plot this blue curve, which is the slope versus gas injected. So the slope is, again, we have this from this plot in the left, and So having the optimum rate, if we have right here the optimum rate or in optimum gas oil production, sorry. So we come here with the slope and cut the blue curve and get the gas injection. So in this case, we have the optimum gas injection for the conditions we are having in the field. So this is a nice way of, showing the managers, this is an analysis based on economics. And um, again, always is good to validate the optimum gas injection with well test. Once we implement the optimum gas, we can tune that, but maybe decreasing and getting the volume of in the production, and so getting at least three or 4 points, additional points. But this, the range is more narrow, so we can still tune out, just to avoid spending excess of of money and resources. In the gas lift troubleshooting area, the main issue is in the gas lift injection is the point of injection. It's the valves or downhole. Maybe we are in the tubing, we are having a hole or something like that. So the injection of the gas is in a different point that we are not really, it was not designed. So we have to face the way, those problems. So the common test to get this is, in case we have communication problems, it's a communication test, is the name of the test. In this way, we can define the faults. We can find which check valves are damaged. Some valves are not properly seated, or leaking completion packers, or anomalous tubing communication. This is, of course, we are dealing with gas, so gas can go through any really small orifice. And maybe we are not getting the optimum, or maybe we are not injecting to the design setting there. The troubleshooting steps we have right here, 3 main areas where the gas leak problems may occur. The inlet is, of course, this is the system, the gas heater, the valves, up to the casing, from the compressor to the casing shop. This is the inlet. Outlet is from the master valve or the wind valve down to the separator. This is what we consider outlet. So it means it's the production from the wellhead down to the separator. Any problem with flow lines and the chokes and everything. So it's considering the outlet. The inlet and outlet are in the surface, and then we have the downhole problems. So I mean, of course, the first area to look is the surface. The gauges should be calibrated, and so everything on the surface should be, checked before going to downhole. Of course, it's cheaper to do repairs on surface than downhole. Downhole we require to call for some maybe, well line or possible well intervention rig. So inlet problems, excessive gas use due to casing pressure, over injection, tubing or collar leak, washout leaf pads. So those are problems that are causing, we are using more gas than we should be using. Shock sizing, maybe we are using the wrong shock size, maybe we are, it's bigger than what we require, or faulty gauges. This is again, hopefully in the fields we have the same type of gauge and calibrated at the same time. Otherwise, we are maybe thinking that we have problems when we have really a gauge problem. And in the inlet problems, high casing pressure is due to gas injection volume, due to partially plugged valves. We are then increasing the pressure because we are restricting the flow. The flowing temperature is changing. Remember that the valves are they are work in the lab under a specific temperature, and the downhole temperature, if is changing too much, we are dealing with the valve problem. Also higher tubing pressure and restriction in the tubing. Those are inlet problems. Also low gas usage. We are not getting, some reason we are not getting, we are not using the volume we are injecting. So we have to confirm with the gas volume injection meter. Of course, verify the operating temperature of the gas lead valves. Otherwise, the valves are not working properly. And test injection flow shock is something that we have to perform. The outlet problems, high back pressure is one of the main indicators of the problem with the outlets. Remember, the outlet is, we are talking from the wellhead down to the separator. Restriction through the choke, debris, or the damage in the choke body. Paraffin or the scale is a very common problem, especially in fields where we have different seasons. Of course, in winter, this is something that we have to face, and so that's why some fields they have to use glycol or another solvent for this type of scale build-up. Flow lines are turning 90 degrees, so airbus, this is not really a best design. Separators operating pressure, the valve restrictions should be fully open and properly designed. Of course, any problem with the flow line, particularly in places where the flow lines are across a road where we have a heavy tracking movement, probably we are facing some flow line problems there. Downhole problems, of course, those are the surface problems are easier to identify, and the approach for the surface downhole problems is through interpretation and the information and we can get from either logins or pressure test, something pressure test. One of the problems is the well is blowing gas dry, so it means we are injecting and the gas is basically bypassing. This is causing pressure exceeding the design operating pressure, tubing communication, the lifting point, and we have to, in this case, verify the inflow from the formation if there is some setting or increase in the gas from the reservoir that initially we didn't consider, or upper valves are operation properly. So in this case, the issue is below those valves. The well is another point with the another issue is the well is not taking input gas, due to maybe the choke is frozen or the gas, the input gas valve is closed with valves on the outlet side. Maybe somebody was doing some maintenance or something like that, and closed the wind valve and left the wind valve in that condition. So maybe you are thinking that we have a problem when it's something that it was, caused by somebody. Feeding problems. Another, the temperature, as I mentioned before, is a problem. So in this case, it is easier to identify because it's a kind of seasonal problem. Also, we have to verify the valve set pressure are not too high for the available casing pressure. Another issue is the well flowing in heads. So it means it's producing high volume and all of the sudden decreasing the production or stopping the production, something like that. So it is not really good. It's not a stable condition. So we have to, maybe the costs are too much or too, we are far from the ideal injection volume. So either too little or too much. The pore size of the valves are too large. The pressure valves are not properly defined or limited feed from the reservoir. That's another issue. Temperature interference higher than expected volume at the beginning. That will cool down the temperature, and then when the conditions will change, when the valves are cooled, they will open again. So this is kind of the reason for this flowing in heads. The well will not unload. Remember that in the gas lift, originally before starting the gas lift injection, the continuous gas lift injection, the system, the wellbore is loaded with either fluid produced or killing fluid. So the fluid column is heavier than the available lift pressure, or the design fluid weight is lighter than the actual weight. So in this case, we are having problems. So another issue is the wellhead back pressure is too high. So we will not be able to unload the well. So, and another potential is the valve is staying open. The sediments in the valves or salt or many issues are keeping the injection valve open. And another is the common issue is the hole in the tubing. So in this case, we have to perform a test, which equalizing the tubing pressure and the casing pressure by closing the valve, and then another issue is low casing pressure and tubing pressure. When the closing wing valve with gas injection is on, the wellhead back pressure is too high, or the valve staying open, sediments against in the valve. Another issue is the valve spacing is too wide. In this case, we have to use an extra source of maybe nitrogen to unload be able to unload the well. And once the well is unloaded, of course, the system will start working properly. So, but if the problem is severe, we have to respace the valve, which is something that we have to pull the tubing. Or a pack of gas leaf is required. Or we have to shoot the tubing to get a new point of injection. So it depends on the situation. We have to evaluate and take the proper decisions. Tuning the well is once we have the continuous production, stable production, we have to consider that to unload the well, we require more gas volume injection than when we are in operation. That's one of the drawbacks of the system, that to unload the well, we need a lot of gas volume, but during the operations, the volume is considerably lower than that initially. So another issue is that the input gas volume can be reduced once the point of injection has been reached. So in this case, we have to start the well on a small input shock, like 8/16, then increase increase the choke size until the maximum flow rate is achieved. We are just optimizing, the well production or gas injection, and so the well production. Of course, by doing this, we have to stabilize the well for at least 24 hours after each change before another adjustment. And in this case, we again, this is the way we have the data for the plot we saw before, in order to optimize the gas injection. This is the way we perform this. And one of the tools that we use regularly is the temperature profile. We run a production logging, or basically temperature logging, and define where is the point of any problem, a gas leak, or probably point of unexpected injection of gas in a point we are not considering. So here we have a log, temperature log. So some questions, of course, as I mentioned at the beginning, the reservoir is an entity is changing. We are producing the well, so the reservoir pressure is changing. The fluids are changing. The GOR are changing. The water cut, of course, are increasing. So what happens if we have an increased water or decreased reservoir gas? So in that case, we have a heavier tubing gradient. It was not originally considered. So in this way, we are lifting from a shallower valve So we are losing, instead of decreasing the borehole pressure, we are increasing that. So we are in the wrong, way. You increase the casing pressure, of course, about the disarm valve. You need to provide more gas to the system than the original was designed. So the question in this case is, do you have that extra gas, or is your compressor able to increase the pressure or the rate? So those are questions that we face in any moment, and we have to be ready to answer this question. And the other situations is, well, of course, it's a natural that we lower the reservoir pressure. Maybe the pressure drop is higher than we were expecting. So what to do in this? We have system that the rate would be lower than the same flowing pressure. So we need to lower, in this case, the borehole pressure, but it means more gas, or higher casing pressure. Or in the case for lower rate for the same surface pressure, so would be right to make a higher tubing pressure for the same depth. So we are affecting the valve mechanics. So maybe we are closing or opening to conditions that we originally we didn't define. So those are issues, the operational issues after we are producing the well for quite some time. We have right here now a brief example, design example, to determine the optimum gas lead ratio given two particular conditions. In a situation where we have an unlimited amount of gas, which is something really ideal, or we are a given amount of, or limited gas amount of gas. So in this case, I'm going to show here. Sorry, is this? The task is define the optimum gas lead ratio given the conditions. Once we define the optimum gas lead ratio, we have to calculate the required injection gas lead ratio. So we have right here this equation. The gas lead ratio to be injected is the optimum minus the gas lead ratio from the formation. So in this case, the gas injection rate to the well is given by this equation, is the gas lead ratio injection times the expected produced liquid rate. So to solve the situation where we have a limited amount of gas available, the potential, the gas lead ratio is given by the gas lead from the formation plus the injection rate divided by the production rate. In this example, we have this information, this data, mid perforations, 5,200 feet, oil gravity, 26 API. So the specific gravity of this oil is 0.9 based on the right here on this 26 API. The gas lead ratio is 300 standard cubic feet per barrel, and so the gradient of this is based on the specific gradient of this particular fluid. And so the IPR, using this IPR equation. So we have the maximum rate is given by 1,500 standard barrels per day. The average pressure is 2,000. 2 in 2.5 OD or 2.259 ID inch tubing. The packer is set at 5,000. Wellhead pressure is basically 200 feet above the mid perforations. Again, the idea is to find the maximum expected oil rate from the well, in case we have this unlimited amount of gas or we have only 1 million standard cubic feet per day available. So the solution is, the maximum oil rate is expected with the gas injection, of course, about the packer. So in this case, we are not considering the friction below the injection point of the packer, which is, it's not a big deal. We are dealing with a short length of tubing. So in this case, the inflow performance curve for the gas injection inside the tubing can be expressed by this equation. This is a function of the rate, the average pressure, reservoir pressure, maximum rate, and the gradient and the setting depth of the perforations and the valve. So again, this is the gradient we got from the API fluid. In this case, we have the valve depth is 5,000 and 5 perforations. Perforation 5,000 and depth of valve 5,200. So with this and with this equation, we calculate those. Basically, this is based on this information. We are using this equation, and so we get for different rates, we get the flowing borehole pressures. With this information, we have to use the Hagedorn and Brown correlation in order to get the pressure loss in the tubing by this fluid type of this fluid with these conditions. And so we have this this information using this. And so with this, we have production rate, the inflow pressure, and the outflow pressure. And so we are able to build this inflow, So inflow and outflow, which is given by inflow, is given by this your production and inflow. And then for the tubing side is the production and the outflow. So here we have the intersection of this plot is given like 632 standard there as rate with the flowing pressure 698. But remember, this is when we have unlimited amount of gas. So this is the operating point. So under this condition, the injection gas lift is the standard cubic feet minus the produced from the reservoir. So required gas injection based on this number then is and the optimum rate is right here. So it's 1,007,775 standard cubic feet per day. So let's see the other case when we have only 1 million standard cubic feet per day. And then in this case, the calculation is given by this equation. Gas leak ratio is the gas leak ratio from the formation plus the gas injected over the rate. So we have right here the gas leak rate versus the rate, and again with this information we have to get the use the Hager-Brown and Brown correlation in order to get the rate and the tubing pressure. And with this, with those new conditions, we have a plot where the rate is about in this case 620, and the tubing pressure is 702. So if we compare this situation where we have only available 1 million standard cubic feet per day, and the previous one here is 632 versus 620 as a production rate. So we see that increasing the rate from 1 million to 1.7.5 million, which is the one we define right here, we are not really, gaining any big difference in the production, only 12 barrels per day. So this is not, I mean, the idea is then use 1 million, and we are saving costs, we are compressing less gas. So in this way we have defined what is the optimum gas leasing ratio. So with this, I hope you guys have ideas, and so I appreciate the time for for coming today, especially the weekend. For some people it's weekend, for other people today is it's a working day. So anyway, I appreciate the time for you guys. Hopefully this those ideas, it gives you some useful information. So anyway, we are able to share more information or answer questions anytime you have those. Please contact the